We're going to talk about analog versus digital. And hopefully, after you watch this video, you will be able to answer to the question, why digital instead of analog? So, in real-world systems, most of the times, at a microscopic level at least, we get the notion of an analog behavior. Some prominent examples include time, acceleration, perhaps some chemical reactions, and the mathematics that come with it tend to represent physical systems as continuous. But then sometimes we tend to, instead of using a continuous notion, we tend to have a discrete behavior like quantum states. And if you're not familiar with that, then when we count mass in terms of number of atoms, from mathematics, some other examples include the number theory, counting, approximating physical systems, and all these are, in essence, discrete. Now, in order to get a better understanding, let's focus on this example of an analog signal on this image on the left and a digital signal on the right. The basis of this difference is that an analog signal is a continuous wave, as you can see in this example, and that this continuous wave changes with time. Now, unlike that, what you see on the right is that a digital signal is just a set of discrete waves that carry data in a binary form. Now, regarding the representation, analog signals are represented usually by a wave that looks like a sine function. On the contrary, what you see here is more like a set of waves that look like squares. Analog signals are described by an amplitude. This is the distance from the x-axis. From a frequency or period, this more or less means how frequent over time you have these waves going up and down. And it's also described by a phase, something that you will learn later on what it is. Unlike that, digital signals are described by the bit rate, which means how many bits are transmitted over time, or the bit intervals. Besides this, another difference is about the range. Digital signals have a finite range, as you can see here. Well, there's no such a notion for analog signals, which do not have a fixed range. Distortion is also another difference between the two. An analog signal is more vulnerable to distortion, and that is a disadvantage compared to digital signals, which are not prone to distortion. And there is a difference when it comes to transmission. An analog signal transmits information in the shape of a wave, as you've seen here. But a digital signal carries data in the binary format, which we describe usually as zeros and ones. It's another example of a zero, that's another example of a one. And finally, the instance. Let's provide a few examples here. The human voice is an example of an analog signal. So an instance of an analog signal example is our human voice. However, a digital signal, on the other hand, is used for the transmission of information to a computer, and that would make it an electronic signal. Now, analog systems are characterized by the following. There is a time-varying input. So the input to the analog signal is between a minimum and a maximum value. And there is also a time-varying output between a minimum y and a maximum y value. Now, there is a relationship between the two, which depends on the function of the analog system and the values of its components. Now, pay attention to this. It's not only the function of the analog system, but it's also the values of its components. In other words, the input. And here is an example of an average calculator through an analog system. Now, if you're not familiar with this is a voltage applied on the one side, another voltage applied to the other side. They both go through two resistances, and this is the result here. Now, if the two resistances are about the same, then the final voltage here will be the average of the two input voltages. This is mathematically described here. This is the mathematical equivalent of what you see in this diagram. Now, this is an example of a different average calculator. Well, it looks the same in the image, but here we have a small difference. In this example, R1 is R2 plus 0.1 R2. In other words, the two resistances are not the same. Now, if you apply, as an example, voltage 1 equal to 3 and voltage 2 equal to 1, the result will not be an average. It will be something close to it, but not exactly the same. So apart from the function here, the functionality, the input values in the system play a role about the final result. That is a characteristic of analog systems. Now, unlike that, digital systems are characterized by discrete time varying inputs and discrete time varying outputs. And here is the big difference. Input and output relationship depends on the function of the digital system. Okay, that's the same as with analog systems. But it's not based on the values of its components. So it's the function of the system and not the values of its components. Same input results always in same output. And that is a big, big difference from analog systems. The system function is therefore immune to components tolerance and aging. By aging, we mean the drift of values. So if you change a little bit the values that you pass to your digital system, the system function is immune to this. The result for the same input will always be the same output. Now, you may be wondering how this is possible. Well, let's consider the example of this switch. Now, in this diagram, what you see is a simple switch along with a control. The way to create a digital system is by building it with switching networks. Now, a switch is an elementary component. It has only two states, 0, or commonly called false, and 1, which in these examples, it is mapped to 0 is mapped to an open switch when no control is applied. And when you apply control to it and you close the switch, then we say that we got 1 or true. Now, by using this elementary component, the switch, we can actually create digital systems. Now, again, you see the switch here, open and closed, and the truth table as we're going to be using in this course. If the control is not activated, just like here, then the switch state remains unchanged, and the other way around. If the control is activated, then the switch changes the position. And this is how we implement a switch in real life. We implement them with metal oxide semiconductors, the so-called MOS. Now, by far the most widely used one is a MOSFET. A MOSFET is the most widely used transistor in digital electronics, as well as in analog circuits. MOSFETs are the basis of high-density integrated circuits, such as memory chips, microprocessors, and millions to even billions of MOSFETs that can be used in order to create memory chips, microprocessors, and so forth. To give you a few more examples, discrete MOSFETs are common for power devices, power suppliers, radio frequency amplifiers, image sensors, display technologies, and many more examples that can come from real life. Now, the mapping between a switch and a semiconductor is as follows. You see that a semiconductor has something that we call a drain. It has a source, and then you got the gate. Now, that is again another representation of a semiconductor. The semiconductors, the MOSFETs come into two different forms. The first flavor is NMOS. Now, what is characteristic about an NMOS is that if low voltage is applied here, then it behaves like an open switch. And on the very contrary, if you apply control here, voltage, then it behaves like a resistance, a small resistance, with negative particles. And the result is an equivalent to a closed switch. Now, the symbol that we use for an NMOS, where obviously N stands for the negative particles, is this. Again, when the voltage applied to the gate is high, the channel is equivalent to a small value resistor, full of negative type particles, and behaves like a closed switch. Now, think of it for a moment. If this is one flavor, then what would the other one be? Well, if you thought about positive particles, you are correct. There are also PMOSs. Now, the main difference here is that when the voltage applied to the gate is low, in this case, the channel is equivalent to a small value resistor again, full of positive particles. So again, the switch is closed, but the difference is that here you got positive particles. And this is the PMOS symbol. Now, if you remember the previous symbol, the difference lies here in this dot-like shape. Now, by using NMOS and PMOS, as you're going to see later on, we can construct more sophisticated circuits. Talking about the electronic signals of logic values, in digital systems, there is a gray area where you've got noise. So in order to identify high value or a high voltage, a logical one, we have to be above some threshold. In this example, is 3.5 volts. Now, if you are below another threshold of 1.5 volts up until, of course, obviously 0 volts, then you got the logic 0. Anything in between is noise, and you cannot tell what exactly the value is. Now, if you want to make this a little bit more reliable and reduce the noise, then you increase the noise margin, such as in this example, where anything between 0 and 1 volts is logic 0, and anything between 4 and 5 volts is logic 1. And the undefined logic level in between is obviously bigger in this case. As we said earlier about digital systems, the same inputs result always in the same outputs. And the system function is immune to components tolerance and aging. And this is because of ignoring the noise in between the two values. The property of immunity comes from that. You can make your system more immune if you increase the noise margin, like in the example over here. Now, concluding this asynchronous video, I would like to summarize the main differences between digital systems and analog systems. In digital systems, you got repeatability of results, as we've seen. Same input will always result in the same output. Unlike that, in analog systems, this is not guaranteed. because analog systems are sensitive to component values and therefore drift and tolerance. Digital systems are easy to design, whereas analog systems, well, you need to be familiar with the fundamental physics. And let's say that if you have experience with both of them, you would realize that digital is always easier than analog. When it comes to functionality, analog systems are suitable for very simple functions, whereas with digital systems, you are capable of constructing complex algorithms that can be implemented with a digital system. And this is also associated to the ability that you got to program a digital system. Whereas in an analog system, you are limited only to some tuning of the parameters.